All right, let's get right into it. We all think we know what a computer program is, right? But what if I told you there are two totally different and equally powerful ways to look at it? One is like seeing the architect's blueprint, and the other is like watching the finished building actually in use.
And this isn't just some dusty academic question. No, this is at the absolute heart of theoretical computer science. The answer reveals this really beautiful duality that actually underpins everything, from the programming languages we use every day to how we can prove that our most critical software is safe.
So here's the split. Is a program the static text we type into a file, a fixed set of rules and grammar? Or is the real program the dynamic, living process that happens when you hit run, the thing you can actually observe and see what it does, moment by moment?
Okay, so let's tackle that first idea. Let's look at a program as just a fixed, structured object. This is the world of blueprints, the world of syntax, grammar, and all those formal rules.
To understand this viewpoint, the tool we reach for is algebra. Now, hang on, I don't mean the solve for X stuff from school. We're talking about a bigger, more general idea of algebra here. Think of it as a system for defining all the legal pieces of a language, like its words, and the very strict rules about how you're allowed to put them together.
This quote here, I know it's a bit dense, but it really gets to the core of it. What it's saying is that a program isn't magic. From this perspective, it's just a precisely constructed object built up from smaller pieces according to a strict grammar, just like a valid sentence is built from words and punctuation.
And this is a perfect illustration of how these algebraic rules actually work. We can take an expression, say x plus 0, and apply a rule that says anything plus 0 is just itself, so we can transform it into just x. And here's the key. We did all of that without ever running the code. We're just reasoning about the blueprint itself.
Okay, enough about the blueprint. Let's flip the coin. What happens when we stop staring at the static code and start watching the building in use? What happens when the program actually runs?
This is the world of Coalgebra. Now, if the first world was algebra, this is its mirror image. Coalgebra couldn't care less about what a program is made of. It only cares about what a program does. It's the mathematics of processes, of states, and of what we can observe from the outside as they change over time.
A traffic light is the perfect, simple example. You don't need to know anything about its internal wiring or circuits. You can describe the whole thing just by its observable states: red, yellow, green, and how it transitions between them. That's it. That's a coalgebra in action.
And this quote really drives the point home. These two perspectives, structure and behavior, algebra and coalgebra, they aren't just interesting little curiosities. They are the fundamental building blocks for how we understand computation itself.
So, we have two totally distinct worlds, the static blueprint and the dynamic behavior. The big question, the million-dollar question, is how do you build a bridge between them? How do you know for sure that the blueprint you designed will result in the building you actually want?
Well, the connection is this really elegant mathematical idea called a bialgebra. And it's basically a single unified object that holds both things at once: the program's static blueprint, its algebra, and a description of its dynamic behavior, its coalgebra. And most importantly, it ensures the two are compatible.
Okay, I know this looks dense, but this one little statement is the absolute linchpin of this entire idea. Seriously, observational equivalence, that's just a fancy way of saying two things behave the same from the outside. And is a congruence, that means our system of rules can treat them as being the same. So all it's saying is this: if two programs act identically, we can officially swap one for the other in our blueprint. It's a guarantee. And this right here is the big payoff. This is where behavior validates the structure. It means our abstract rules aren't just floating around in theory, they are directly tied to real-world results. If the results are the same, the pieces of the blueprint are interchangeable. So why do we care about any of this? Well, this isn't just an abstract math exercise. This unified view, this bridge between rules and results, is precisely what makes modern, reliable software even possible.
I mean, think about it. By formally connecting rules to behavior, we can mathematically prove a program will do what we want it to. This is how online banking can verify that two simultaneous transactions can't possibly corrupt your account balance. It lets us design languages where whole categories of nasty bugs, like race conditions, are simply impossible to write in the first place. It ensures that critical systems, in aviation or finance, aren't just tested, they're proven correct.
Ultimately, this powerful duality gives us the confidence to truly reason about software.
It builds that solid bridge from the abstract symbols sitting in a text file to the concrete, observable actions of a program running out in the real world, and it makes sure they match up perfectly.
And this leaves us with a fascinating, kind of mind-bending question for the future. We've seen how behavior can validate the structure we write. But what if we started the other way around? What if the next great programming language wasn't designed by writing rules, but by simply describing the behavior we want to see?